Thank you very much for your invitation. So, can I start my keynote?
Yes, please go ahead.
Okay, thank you. So, I will present you this keynote modeling and simulation methods for optimized location and size of distributed generators systems. And I present also a little appendix about hybridization concept for horizontal axis wind and tidal system using real-time emulation method. So this work is realized with my previous PhD student, Dr. Ahmed Alameri, and Dr. Mohamed Ashglaf. As you know, I work in University Le Havre, Normandy, in groupe de recherche en électrotechnique et automatique du Havre, research group in electrical engineering and automatics from Le Havre. So just a little, I have a little problem. Just a little presentation about these labs. There are three research team, electrical energy systems, operational safety of industrial systems, and one team that ties two previous related teams, renewable energy and systems. So the main field of research and application, smart grid, production of electrical energy from wind energy, tidal energy, photovoltaic fuel cell, etc. So some research access in transport and real-time control for industrial application. So my speech will be structured in some steps. For the beginning, in the case of modeling and simulation method for optimized location and size of distributed generator systems. So you'll see in the screen that I propose you some discussion of general discussion, not very long, about electrical power system, distributed generation. I will see with you the main research objective, what are the optimization methods, some results, and finally some idea about using real-time emulation, hardware the loop simulation, and our perspective and future works. As you know, for the power system analysis in the past decade, distributed generator DG has become one of the fastest growing technology, and is expected that that development to continue. Interconnecting DGs to an existing distribution system is means to increase and fulfill the yearly electrical energy growth in demand. Distributed generator could provide various benefits such as power quality enhancement, loss reduction, voltage profile improvement. However, the planning and operation of distribution network are facing different challenge when more DG, distributed generator, is connected. The network planner should consider the positive and negative effects of distribution generators when an efficient network is designed with a high penetration level of DG. So therefore, why the optimal location, sizing, and type of DG can give guidance to designer on and the operator to achieve the performance of the grid. Finding the optimal size and location correspond to optimizing the operation and planning of electrical distribution network, taking into account capacity of distributed generators units as constraint. Thus, for accurate solution for optimization problem is more important to operating planning that also the time of calculation. On the contrary, near optimal speed up time calculation to solve the problem for operation can be useful also for DSO distribution system operators of real-time operation. This for why, in addition to planning for size and placement of distributed generator required, the type of this kind of new sources must be considered. For example, wind energy differs for the other sources, and a large scale now of onshore and offshore wind farms could be give some problems that arise when these kind of sources for a high level of power to be in consideration. Because the improper placement of VFAR, for example, could increase the real power losses in the distribution system. This is the old problem about this. There is no, it's a problem. The problem that in the last year arrives, and that's why we try to find some optimization methods and for size and for placement of DGs in grid. That's for why I present you some selected main methodology that we used. This will be a little complex because I selected that we consider the main technologies that could be used in this case. That's for why, for the beginning, we try to present you the scope and the main objectives of our works. The first objective is to explore the application of a number of approaches in the area of power system analysis. The second objective is to develop linear models suitable for the prediction of optimal distributed generator size. Since the active power has strong coupling with the voltage angle in the power system, we consider that the method called fast predicted linear model should be used to estimate the real power losses. Moreover, faster and acceptable accuracy calculation must be efficient tools for grid operator to assess the power system with a large scale DG connected. The third objective is to investigate the impact of DG size of, on real power losses into grid. Since fast predicted linear model cause error in estimating optimal DG size, we must extend the methodology to analyze multi-DGs unit based on, for example, wind energy resources, as well as finding the optimal placement of each DG as a part of the future or actual network. The four objectives of our work concern the requirements for integration of DGs in the actual grids. And for this, we try to find optimal solution, global and local solution for power system integration. And it will be, if you want, the last part of the research objective to be accomplished. The final objective is finally to demonstrate that we'll can use the mathematical tools, very complex in mathematical tools, to find the optimal size and the location of this kind of new sources. So, for example, in this slide, we show that we can use the famous, well, we can say the sure complement. There's an algorithm that we tested with several ISER benchmark test system, and we compared the result with the Newton-Raphson method or fast decoupling method in order to find more time for computation, to give to the operators and to the people that manage this type of energy, to find with the command control unit the optimal solution. We introduce a new in this approach what we call a new algorithm, run-length encoded, that is extracted from representing data using meta files. So this method is proposed for to transform the dimension of the matrix, very hard to implement and manage in computing, in vector. So instead of two-dimension matrix, we will try to have a vector that could be manage more easier. Another method for optimization that we use in for integrating multiple distributed generators is to linearize the power flow, and we obtain what we call the simplified power laws method. This is well know this kind of simplification. So linear equation modeling will be used in our approach to simplify power loss calculation. This calculation, in this case, this calculation with simplified power losses calculation could accelerate the processes to predicate optimal DG size. So each location of DG at load basis has optimal size, and the objective of calculus will be minimum power losses. We also use, because this is a modern method, the genetic algorithm technique. We obtain good results. Two optimization technique we develop: local and global optimization, using also the linearized calculation for real power losses. This algorithm is implemented to find the optimal location and side for also for DG unit in the grid. For this, we develop our algorithm using the mathematical complex mathematical aspects is fitting formula and so on. We also use the anterior point optimization method in order to also to gain the memory, CPU memory, and time computing. And finally, we try to use the performance tools, that is the Kalman filter, that will be compared with another, the previous element that I show you. So perhaps it's difficult to understand for the beginning our approach, global approach. We'll try to find what will be the mathematical tools to select the location of distributed generations, or the size of the DG size, the size of DG or distributed generators. So for example, using the Kalman filter, the obtaining results show that the developed estimation method could save more than 60% of required execution time when compared to an existing method based in Newton-Raphson method. This time saving advantage is achieved at the expense of only a small error in estimation both the minimum power losses and the DG size. I regard the time. So this is one simulation for the 5 I3 bars. So some results. So for example, here we tested the time reduction using the Shure method. Shure method testing in we've tested by 4 systems, and we compare the result with Newton-Raphson method and fast decoupling method that I told you before. The results show good accuracy with less memory and time. Here we have the results. Another results, we make the comparison results of iteration between, we can say in comma, normal and run length encoding method. So the number of iteration decreases. So we have what we call the time reduction for this kind of method. So results here that we see on the slide show the efficiency of RLE algorithm because we reduce consequently the iteration numbers. So we note also that the time required to implement this calculation is decreased, and in this case we can optimize the CPU execution time, and the number the calculation will be done with less memory. So in this slide we have different results where the distribution generator are located differently. For example, here we have 14 buses losses with different DG location. So we could make this comparison with the linear method Newton using algorithm Newton-Raphson. So there are some difference that we'll see after this slide. This difference, for example, the obtaining minimum power loss point of each DG placement represent here the optimal DG size. So we can it can be noticed that the system behavior follows the system input. So the size of DGs. This comparison between Kalman filter and Newton-Raphson method could be interesting for the performance comparison for different locations. So we have two objectives where we can place the new farm, wind farm, and where and what will be the size of wind farm. It's important because we can fortunately we can compare with power losses. Another result, for example, here, results of optimal size and location of multi-DGs by genetic algorithm. For example, for this 14 I-third basis, maximum losses in line before DG is about 4.2 megawatt, and after placing DG is about 1.7 megawatt. So it's important to find the site and location it is possible in a real time. So for this, we must have more time for calculation of this complex element. The time, okay. Some word of impact, for example, wind farm in on electrical power with when we have also variable load simulation. Because the growth of electrical demand increased and the need of wind energy sources increased, but we must handle it. The size and location of wind farm is selected depending on the analytical model explained a little in my intervention here. We try to simulate 5 wind farm about 45 megawatt, and the results are very interesting here. Sorry. The results are interesting because for example, for the case of the 5-bus system, the fluctuation of the wind power output due to the wind speed variation could change the calculation of total real power losses within 30–40%. So in this case, the less computation time compared with the global optimization with genetic algorithm could give good results, like you see in this part of this slide. So where we have loss without farm and loss with farm, we see that if the location, the size is well done, well calculated, we can reduce the power losses. In conclusion, for this part, there are a lot of methods that are we propose in this work. So starting from linear power analysis and the simplified loss model, and using Kalman filter or genetic algorithm or interior point, so we can find fast GG size, global optimal location L size, and for the last cases, less computing time. That's for why it's a little complex to present directly this result. So we try to obtain some steps step by step to arrive for global and local optimal location, size also, and for multi-DG unit with a flexible constraints and with less computing time. So for this part, this work, evidently, that in this slide, I make a little resume about impact of distribution generated and the wind energy into grid. There are some results. For this, in order to have validate this method, so we have online. We must have. We have to work with monitoring the operation of grid. So we will try to make this algorithm with our colleague from one university in Romania, one university for Germany. My iPhone said that I have 30 minutes. So there are a lot of things about this. For the second part, I make very quickly. It is possible?
Perhaps now, because you have just 2 or 3 minutes, if you can.
3 minutes. So some problematics of hybridization concept for horizontal axis wind and tidal system using a real-time emulation method. What is research? What objective you see here? We try to study what we call hybrid wind and tidal power generator system. So for this, we are based in the function similarity of wind tidal turbine horizontal axis. So we used what we called the concept of electromechanical coupling of hybrid wind tidal power system. We dared to have one idea with some colleague of Ina University from South Korea. As you see here, the principle of this concept is based on the integration of the mechanical torque generated by the rotation of tidal and wind turbine in the same transmission shaft. So you have, fortunately, the possibility to validate, and we validate the feasibility of this concept, electrically speaking, because this concept is difficult to realize from mechanical part. You know that we have in our laboratory, in GREA laboratory, what we call an experimental performance structure, hardware is a loop simulation. And here you have this experimental platform that you have here, the platform, electrical platform in our laboratory, and this side we have the little platform realized by our colleague from Ina University. So the principle is here. If I have present you some results, yeah. So obtain it in experimental simulation. So we'll see that we can emulate 2 turbines. In the left side, we have wind turbines. Right side, we have tidal turbine, and we have camshaft with asynchronous generator, double feed asynchronous generator connected to the grid. So the results are obtained also with what we call in accelerated time, because the problem from the wind and the tidal sources, there are a lot of data, and we validate algorithm that allow us to decrease the number of data with evidently some errors in the output power, but we have these tools to realize finally for a little power rate this control strategy. So
please, Christian, if you could conclude.
So thank you. Thank you very much.